Question, why does this work? Why can we find equations of tangent planes in this way to do linearizations? And the answer to that is, well, let's think about equations, let's back off of equation of tangent plane, just think about equations of planes. So for equations of planes, we know we need two things. We need a point and we need a normal vector. And we also know from past experience that the normal vector we often find by take the cross product of two non-parallel lines in the plane. Okay, so we want to think about this, and we can think about, for finding the equation of a tangent plane, we can find a point, and we can find two parallel lines that lie in the plane. Well, we should be able to find an equation of the plane, and we should be able to end up with the same thing that we got before. Okay, so let's draw some axes here. We have some surface floating around in our three-dimensional space. When we have at this particular point, say this is P, we have our tangent plane here. Okay, so first off, what is this point? Let's say that the coordinates of so let's first off say that here that this is the graph of z is equal to f of x, y. And if the point here P is if the x coordinate is a particular value A, the y coordinate is a particular value B, the z coordinate is going to be f of AB. So we have our point. This is going to come in normal. Sorry, come in handy. Now we need two non-parallel lines in the plane. Okay, and so to do this, what we're going to do is that we're going to think about two non-parallel lines. They will give us vectors here. We're going to think about, slicing this along the x-axis, slicing this along the y, parallel to the x-axis, parallel to the y-axis. Okay, so the first thing that we want to do is, I think I'm going to have to go to a new slide for this, is slice this so that we have the graph moving. So remember, this is going to be the positive x direction here. What happens if we just slice this at, here is our point P, so that we are moving in the positive x direction? Well, if we go in this direction here, we're going to, and for this is our, let's say some vector v. V is corresponding to, let's say that we move 1 unit in the positive x direction. We're going to move parallel to the x-axis, and so in particular we're not going to change the y coordinate at all, so 0 units in the y direction. And what about in the z direction? In the z direction, we're going to move f sub x, a partial derivative of f with respect to x units in the z direction. Because, this picture here is corresponding if we draw something in the xz plane, that at this point, here again is our point P, we're going to move 1 unit in the x direction, and so this is going to be 1 unit here, and f sub x units, I guess here, f sub x, the partial derivative I'm drawing to be negative here, f sub x units in the z direction. So this gives us a vector that lies parallel to the plane. V is 1, 0, and the partial derivative of f with respect to x. Okay, but now we can think about if we do the same thing for, let's call a let's say that we have a vector w. So what's going on with w is let's move we'll move 0 units in the x direction. We'll move 1 unit in the y direction, positive y direction. And then, so here the graph is going to look very, very similar. We're just going to draw the YZ plane here. Here is our point. We move 1 unit in this direction. How much do we go up? The partial derivative f with respect to y. So we have found a second vector here. V is 1, 0, the partial derivative of f with respect to x. W is 0, 1, f sub y here. And so now, guess what? We have our point, and we have 2 non-parallel vectors. That will give us these 2 non-parallel lines in that lie in this plane. So we can take the cross product of these two, get the normal vector, use our point, come up with the equation of the tangent plane. Let's see what happens there. So our normal vector is going to be, take the cross product I hat, j hat, k hat. Our first vector v is 1, 0, f sub x. 1, 0, f sub x. Second one, 0, 1, f sub y. Okay, so let's take the partial derivative, sorry, not the partial derivative, the determinant here. I hat times 0 times f sub y minus 1 times f sub x. So I hat times negative the x partial derivative minus j hat, cross out the top row and second column, 1 times f sub y minus f sub x times 0, plus k hat times 1 times 1 minus 0 times 0. And so this ends up as minus f sub x I hat minus f sub y j hat plus 1 times k hat. Okay. Now, really, what at this point we're thinking about, once again, our point P is A, B, f of A, B. So really, all of these partial derivatives, both of these partial derivatives need to be evaluated at the point A, comma, B. So this is really going to be negative x partial derivative at AB, negative y partial derivative at AB, and 1. So we have a point, we have our normal vector here, so we can write down the equation of our plane, which is going to be negative of the x partial derivative value at AB times x minus a minus the y partial derivative value at AB times y minus b plus 1 times z minus, the z coordinate here is f of a, b, is equal to 0. And so this is our equation of the tangent plane. Now, this looks different. This looks different, but what we can do is that we can rearrange it. We can rearrange it by moving. There are 1, 2, and 3 terms here that all come with negative signs. Let's move all 3 of those terms to the right. So the only thing that's left on the left is z. So z is equal to, move this to the right, f of a, b, plus, move this to the right, f sub x of a, b times x minus a, plus move this to the right, f sub y of a, b times y minus b. And this is the formula for the equation of a tangent plane that we came up with before.